The handouts I gave you are just kind of to help you today while we're talking about this stuff. So you can just sort of fill in the blanks here and save this in your notes. We're gonna start talking about polynomials today. Okay, polynomials are a big deal. Polynomials. I'll explain what they are in a second. But in math, they come up a lot. I mean, a lot of what we do in math is we want to use math to build models that describe the real world. And polynomials are very good at that. So what's a polynomial? This is, if you look on the first page of your handout, I didn't put everything on this slide I've got on the board up here. Look where it says, in general, a polynomial of function degree n has the standard form, this, right? This is a polynomial, general polynomial in standard form. Okay, so what's that mean? If you keep reading in here, it's going to tell you that the coefficients, notice that we have, in each case, each of these terms is going to have an x or a power of x, and then it's got some number multiplied by x. So that's what all the a's stand for. They're the coefficients, right? So a sub n is going to be the coefficient of x to the n, whatever n is. N's just going to be some number, right? A sub n minus 1 is the coefficient of the x to the n minus 1 term, and so on. What's it mean when we have like the plus and the 3 dots there? What do you think that means? There's more, yeah. So what's it? We're just kind of continuing that pattern as long as we need to, right? Because n could be 1,000, but I don't want to write out 1,001 terms. And so we'll just assume that, we just keep following this pattern all the way on down to the end, right? But it's the same pattern every time, okay? So it just means kind of like, et cetera, et cetera. All right, so what are the characteristics of this? Well, if you in the reading, it'll tell you, and it's all right there for you. The coefficients are just real numbers, any real numbers. Could be weird real numbers, could be square roots, could be fractions, could be decimals, could be irrationals like pi or square root of 2 or something like that. The only thing they can't be is a complex number with an imaginary part. So you can't have i's in there. But everything else is fair game for the coefficients of the powers of x. What about the n's? So the exponents. The exponents in a polynomial, the powers of x, are going to be whole numbers. They can't be negative, but they could be either be 0 or all of the positive integers, right? So if we were to write sort of the invisible or missing powers of x down, what's the power of x right there? X, if I just write a plain old x, it's implied that it's to what power? The first, good. And then I didn't write it, but if I wanted to, I could write an x to what power at the end? It doesn't even, the x doesn't even show up. So what power must it be to? No. No. 0, right, because anything to the 0 is equal to what? 1, right? And so then a sub 0 times 1, x to the 0 is 1, is the same thing as a sub 0. So the pattern actually does continue all the way out to the last term. We just don't really write the x to the 0 or the 1 in that exponent, right, in x to the 1. But it's the same pattern, right? We're going to step down, like, for example, if n is 6, then we'd have an x to the 6th term, some number times x to the 6th, plus some number times x to the 5th, right? 6 minus 1, plus some number times x to the 4th, plus some number times x cubed, plus some number times x squared, plus some number times x, plus some constant, right? Now, it could be that we're missing, maybe one or more of those coefficients are 0, and so the terms just disappear completely. But we could have all of those terms if n is equal to 6. Does that make sense? Okay, so what's an example of a polynomial? Well, here's an example. That's a polynomial, right? What's polynomial mean? Poly means many, nomials mean terms. So it's just the sum of a bunch of terms, and each term is just going to be a number, some coefficient, times the power of x. When we write it in standard form, we're always going to write the powers of x in decreasing order. So the biggest power of x comes first, then the next biggest power of x, et cetera, et cetera. Okay? So that's a polynomial, all right? We're gonna do some exploration of polynomials. Today, though, the goal for the day is we just want to kind of understand sort of what the pieces of a polynomial look like, and hopefully, we'll see if we can get there. We want to maybe look at how we could identify what the end behavior of a polynomial is going to be. Okay, and so to get there, let's look at some power functions. Right, instead of looking at just a whole bunch of terms, we're just going to look at single terms for now. This is called a power function. If f of x just equals x to some power, call that a power function. So let's fill in this table. This is some stuff that we talked a lot about back in Module 1. And if Module 1 it's probably not, it's been a while, you may be a little rusty, and it may be that you had some holes when we were going through Module 1. Maybe you didn't understand everything completely. This will fix that. This is the way math is. A lot of times in math, the first time through, if things aren't totally clear, by the time you roll through it a second time, your brain has some prior knowledge to leverage when you're learning the new material. You're able to scaffold the learning, and it just becomes so much more easily. So you'll fill in some blanks maybe. Okay, let's look at these functions, and we're going to look through Desmos. We're going to graph these things, and we're just going to get a domain and a range, and we're going to look at end behavior. Okay, kind of refresh our thinking about what these things mean. So if we go through these. Okay, so y to the x, we know what that looks like, right? Just a line. In slope-intercept form, it's just y equals 1x plus 0, right? mx plus b. The slope is 1, the y-intercept is 0, voila. There's our line, okay? So let's fill in the blanks then. If that's what it looks like, what's the domain? What's the domain of that function? What's domain mean again? You gotta probably define that. Domain and range go together. Other way around. Think alphabetical. X before y, d before r. So the domain is the set of all the x values that work in a function that we could input, and the y is the range is the set of all the output y values, right? So what are the x values that work in this function? Is there any limit? You could go forever to the left on this function or forever to the right, couldn't you? Agreed? So what is it? Negative infinity to positive, all reals, right? It's everything. So written in interval notation, we'd say it's going to be from negative infinity to positive infinity. What about the range? Same thing, right? There's no limits on the y's. You could go as far down as you want to go. You'd have to walk to the left to do that, but there's no limit to how low you could go, and there's no limit to how high you could go, right? Everybody agree? So if we fill these in then, yeah. Okay, now what about this stuff here? Let's look at this end behavior. It's been a while since we talked about this, but what's this mean? As x approaches positive infinity, I'm going to really need the positive there, but as x approaches infinity, f of x, which is a fancy name for y, approaches what? What is that saying? In which direction is the ant walking if he's approaching positive infinity? To the right, isn't it? Right? The x-axis goes horizontally in the positive direction and the negative direction. Right? Negative is to the left, positive is to the right. Okay, so if we look at our picture then, our graph, as the ant walks to the right forever, what's his y value doing? It's approaching infinity. As he goes to the right, he's going up, right? What about as the ant walks, as x approaches negative infinity, meaning as he goes to the left forever, what's happening vertically? Well, it's going to negative infinity, right? So we can fill those in. Positive infinity, negative infinity, right? Everybody agree? Okay. Next line, let's look at x squared. So if I turn on x squared, that's the red parabola, right? And we knew that's what it was going to look like. We know x squared is a parabola. What's the domain going to be this time? What do you think, Lacey? What's the domain going to be for the red function? Values of x. To, yeah, from where to where? Positive infinity on the right. Yeah, there's no limit. The ant could go as far to the right as he wants to. What about the left? Same, negative infinity, right? So there's no limitation. Once again, there's no restriction on this. The ant could go, I mean, sure, he's going to be moving vertically at the same time, but you get what I mean by that. If he keeps walking to the right, yeah, he's going to go up forever, but he's always going to inch to the right. There's no limit to how far right he could go, is there? See what I'm saying? What about the range, though? Nick, what's going on with the range here? Is there a minimum y value? Is there a lowest y value? What's that going to be? 0. Aha. So the ant could stand at a point where his y value is 0, but he couldn't go any lower than that. Agreed? Okay. What about vertically up from there, though? Infinity, right? Good. So it's going to be all values of y. What then? Greater than. Not just greater than, though. Or equal to. Greater than or equal to 0, right? Okay. So we said no restrictions on the domain, but our range was restricted. It had a lower limit. What about the end behavior? As the ant, or as x approaches positive infinity, what's y do? Positive infinity. As x approaches negative infinity, what's y do? Positive infinity, right? Okay, x cubed. Let's look at x cubed. I'll turn these off for a second. So x cubed, all right. What's the domain going to be? What do you think, Bailey? Domain. Negative infinity to positive infinity. No restrictions, right? Okay. What about the range? What do you think? Negative infinity to positive infinity. No limits vertically either, right? Okay, what about the end behavior while we're at it? As the ant goes to the right, as x approaches positive infinity, y goes positive infinity. As x approaches negative infinity, y approaches negative. Now, if I look in my table, that looks familiar, doesn't it? Which row is that like? Yeah, it looks like that's the blue row, isn't it? Right? This is going to be the same as f of x equals x. Okay. We want to make a prediction about x to the fourth. It's going to be the same as x to the second. Let's check that out. Okay, notice that what we just said a second ago, that x and x cubed looked pretty similar, didn't they? Okay, same basic behavior. Well, let's compare x squared to x to the fourth. Pretty similar, right? Everybody agree? Oops, what am I doing? Okay, what's another row on there that might look similar to those two? X to the sixth. Okay, what's the trend? What's it doing? Okay, so all the even exponents are going to be the same, and all the odd exponents are going to be the same. Now, what's really, if you look at what's specifically happening, even if we compare the even ones, what's going on? The red one is x squared, the green one is x to the fourth, and the purple one is x to the sixth. Can you? Yeah, their shape is changing subtly. They all look pretty similar, right? But wouldn't you agree that the green one, if I go out to, and this makes sense, if I go out to big values of x, shouldn't, like for example, when x equals 2, the red graph is going to be at x equals 4, 2 squared. where's the green graph going to be at? X to the fourth. It's going to be a lot higher, isn't it? Because 2 to the fourth is 16 instead of 2 squared is 4, right? So doesn't that mean that the green one's going to have to be a lot steeper? Because it's got to climb higher. It's got to get to a higher point when we get to x equals 2. Everybody seeing that? Manuel, you seeing that? Okay. Same thing if I go backwards, right? If I go back to -2, x squared would be at 4, but the green one has to get all the way up to 16. What about x to the 6th? That's got to get up to 64, right? So it's got to be even steeper yet. What about in here, though? How come, like if I were to go to, for example, 1/2. At 1/2, what's 1/2 squared? It's 1/2 times 1/2, 1/4. So the red one, if I go over in the x direction 1/2, I have to go up 1/4. What about the green one, though? I'm taking it to the 4th power. So 1/2 to the 4th power is going to be what? That's like 1/2 times 1/2 times 1/2 times. So it's 1/2 to the 4th is the same as 1/4 squared, isn't it? Right. So 1/16. Well, yeah. Look how much lower that one's got to be then, right? Because for values of x that are less than 1, when I take them to higher powers, they actually get smaller, don't they? Right. For example, 0.1 squared is 0.01, but 0.1 cubed is 0.001. Right. See what I'm getting at? And so it's gonna cause this green function to be kind of more boxy. It's gonna be more squared off at the bottom, but then steeper on the sides. And if I go to x to the 6th, even more so, right? What do you think is gonna happen? Well, here, I'm gonna pose this a little differently. So how many people are involved in music in some way? Anybody? Okay. Maybe that just means, you probably more people would raise their hands, but how many people like music? Okay, so music is a big deal. It's a big part in our lives. In physics, we talked about music. Music is very mathematical, extremely mathematical. It's not a coincidence that if you look at people that are really good at music, typically they're also really good naturally at math, and vice versa. Music is just exploring sound in this case. What is sound? Sound's a wave. It's just a wave. That's all it is, right? And so if we were to graph what a sound wave looks like, if we were going to look at, it's just a pressure wave. If we wanted to look at something like pressure as a function of time, because really all it is, if I snap my fingers, it's just a sound wave that's emanating. There's a little pressure wave that's going to cascade out spherically at your eardrum, and that's how you hear it, right? But one way to represent that is, it's kind of interesting. I had to humor me here for a second. One way to look at that would be on a graph, where we could look at pressure as a function of time, and then the sound wave would just look kind of like this. It's just a wave. So there are different parts of sound that we have really good ears for discriminating differences in sound. Everybody knows if I talk about pitch, or you know what I'm talking about, like a pitch. Like everybody sings law, you can sing law and it would have the same pitch, but it sounds different because your voice is different than mine, right? Same thing for instruments. If I play a C on a trumpet and I play the same note on a piano or the same note on a guitar or on an electric guitar, I'm going to get different sounds. Why do they sound different? They sound the same. We all recognize it's the same note, but they have different timbres, what we'd say in music, right? It's just the shape of the wave. So the wavelength corresponds to what the pitch is, right? But the shape of the wave corresponds to what the sound of the tone is, right? So this might be, for example, let's just say hypothetically that's a trumpet. Then a piano might sound more like this. It's going to have a different shape to it, but it's going to have the same wavelength, right? So if you were creating, let's say a synthesizer, and if you've ever messed around with a synthesizer, they're kind of fun. You can push a button and say, okay, I want to make a sound that's like a trumpet, right? You push the trumpet button, and then if you play a note, it sounds like a trumpet. If I want to make it sound like a guitar, it'll make it sound like a guitar, etc. You can even do weird things like you could make it sound like breaking glass, or you could make it sound like a really pure tone, right? A really thin, pure tone that doesn't have the overtones and all the little bumpies on it. And that's really what that blue wave would have been. So if you want to use a synthesizer to create these extra sounds in music, really all you're doing is you're controlling the shape of the waveform. That's it. Well, look what we're doing here. This is kind of the first step in that kind of thinking, is what we did right here, right? If I want to have a rounder tone that's going to be, it really does sound, you described it, if you heard it, you'd say, yeah, that does sound kind of like a rounder tone. It's a little softer. It's going to be more like the red waveform. But if I want to have like a really pure, thin, pure synthesizer kind of a sound, we want it to be more squared off. So internally, inside the programming in the synthesizer, what's it doing if we want to create a much thinner, purer tone? What am I going to do to the power of x in this polynomial? And that's what they're doing. They're using polynomials to generate these waves. What's going to happen if I do something like x to the 1,000? What's it going to look like? See what I'm saying? Look what that did. It created a square wave, right? So that's how the synthesizer is going to make a really, really pure sound. But if I want to make something that's, that's a lot rounder, I can just make it an x squared, right? Get the idea? Okay, well, there's my little tangent. Okay, so where are we at with this? So we were able to fill in all the blanks on this guy, and you correctly saw that this is going to be red, right? This row is going to be red, and that row is going to be red, and the odd ones are going to be blue. Okay? Let's talk about symmetry for just a second also. Even though that doesn't really come up a lot in this section, it's something that you're going to deal with in the future, and we've talked about it in the past. Let's look at the symmetry of these guys. So, do you remember when we talked earlier in the year about even and odd symmetry? What was even symmetry? Do you remember? Graphically speaking, what was even symmetry? There was a functional test we had, f of negative x equals something, but I don't want to go into that. Let's just talk about the graphs. What kind of symmetry were we talking about? We're talking about even symmetry. Now, I'll give you a hint. Here's an example of a function that shows that. You tell me what's going on here. X squared. That's a classic case of even symmetry. So what do you think? What kind of symmetry does that have? Say it again. Bilateral, which would be the same thing as, like, we could say folding symmetry or reflective symmetry. Hannah, you got your phone going on back there? If so, please put it away. Okay. Now look up here. So we got folding symmetry about the y-axis, don't we? Okay, that's what we mean by even symmetry. Is it's going to be folding symmetry about the y-axis, right? Can you think of another function that's going to have that? X squared did. What else? What do you think? It's got to have folding symmetry about the y-axis. Would you agree that if I folded this thing onto itself over the y-axis, it'd overlap? Give me another row that's going to do that. X to the fourth. X to the fourth. X to the sixth. Bingo. Well, why do you suppose we call it even symmetry, maybe? Because they're even powers of x, right? Okay, what was odd symmetry? That was different. Let's take an example of odd symmetry. Let's look at x cubed. Odd symmetry was not folding symmetry. You can't fold this function on itself. It's impossible. But what can you do to make it overlap? This was a little different. This is one that was probably a little harder. You guys hadn't probably seen a lot of this before. But odd symmetry is rotational symmetry. So if I put a tack at the origin, I could spin this thing around half a turn and it would overlap, right? That's what we mean by odd symmetry. Well, give me another function up there that you think is going to have odd symmetry. X to the fifth. Sure enough. Same thing, right? What's another one? X to the 1, or just x, right? All of those have that rotational symmetry. Okay? Good? All right, so next step. Next step. What if we wanted to tweak these a little bit? What if we want to go take each of those and multiply them by -1? There's a couple ways we can look at this. think back to, once again, to Module 1. What happened when we did transformations of a function and we multiplied the function by -1? What did that always do? Did something important. It made it negative, right? When we multiplied something by a number, it stretched it vertically, didn't it? But when it was negative, it did something else. So let's see what happens. You make a prediction for me in Desmos here. If I take, for example, let's just look at x cubed. If I put a negative in front, what's it going to do? It's not going to shrink it. It's not going to shrink it. What do you mean by that, Tyler? Flip it over what? Not the y-axis. It's gonna. I can see it's gonna look kind of like it did that, but it's not doing that. It's flipping it over the x-axis. It's gonna reflect it over the x-axis. Okay. In this case, it might look like could be either one, but let's give maybe a different example. If I turn on x squared, same thing, right? If I put the negative in front, clearly with the x squared, it's reflected over the x-axis, right? So each one of those, it's going to accomplish the same thing, isn't it? If I put the negative in front, it's just going to reflect it over the x-axis. Okay, agreed? There they all are. So what's that going to do to the end behaviors? Let's look at the odd functions for a second, just the odd functions. What did that do to the end behaviors? Maybe let's just focus on one of them, because they all do essentially the same thing. Right? There's x cubed, and there's negative x cubed. What did it do? As x, yeah, it just flips them, doesn't it? As the ant goes to the right now, as x approaches positive infinity, instead of going up, it goes down, and vice versa. Right? So if we were filling in our table, it's just going to switch those around. For an odd function, what's the domain and range going to be? Are there any restrictions? No. So an odd function is still going to have infinite domain and range, right? But the end behavior is going to be switched. Okay? What about an even function? Let's take x to the fourth. There's x to the fourth. There's negative x to the fourth. So what did it do to the end behaviors?
The maximum is 0, or the maximum is 0, but the minimum
Is right. So the minimum goes down forever in this case. So it just changed the signs of both of the end behaviors. So when we go to the right, it goes down. Go to the left, it goes down. Domain is still infinite, but what did it do to the range? It goes, yeah, what's the range going to be for this function now? So if I went on my original table to all of the, I can't remember what color they were. If I went to all of the red rows, the even rows, what's it going to do to the range? Instead of being all values greater than or equal to 0, it's going to be less than or equal to 0. Right, so this one would have been changed to be this. It would have gone, from like that, right? Okay, make sense? Okay. So that's one way to think about it. That's a good way to think about it. We thought about it in terms of a transformation, flipping a function, but there's a different way to do this, different way to think about this that I want you to get used to. This is what we're doing in calculus right now. Kind of a higher level, but it's the same kind of thinking that's important. And I always try to do this, just so you know. I teach different levels of math. I've taught higher level college calculus, and I always try to think about where you're going to go next with this stuff. And so I don't just want you to be able to do the homework that we're doing now. I want you to be able to take this with you into the future and have this prior knowledge that's going to make it easy to do the next level of math. And so there's another way we got to look at this, at finding these end behaviors, other than just flipping the graph. Think about it this way. Let's take a function like f of x equals, let's try something like negative 2x cubed, for example. And let's try to find the end behavior without using a graph. Okay? As x approaches positive infinity, f of x approaches what? Now let's think about this. If x is approaching positive infinity. Infinity is not a number, right? But as we approach positive infinity, we're starting to get x values that are huge and positive, right? So if we do something like, this is going to be, and this isn't technically even correct, but if I were to try to evaluate this function at infinity, let's evaluate it at 2 once, just to get the idea of what we're doing. What if I do f of 2? Where do I put the 2 in my function? If f of x equals negative 2x cubed, what's f of 2 going to be? What's that mean? I'm just plugging 2 in for x, right? That's in math how we say, what's the value of the function going to be when x becomes 2? So where would I plug that 2 in? For x, right? So that would just look like negative 2 times 2 cubed, right? Everybody see? What about that? That's weird. F of infinity. You can't really do that, but we get the idea. It just means really big numbers, right? So what's that going to give me? It's going to give me 2 factors. The first one is going to be negative 2, and the second one is going to be positive infinity cubed. Weird. You can't cube infinity, really, but you can cube big numbers that approach infinity. So what are the signs going to be of those? Well, the first one is just going to be, it's going to be plain old negative 2, isn't it? What's infinity cubed? What do you think? It's infinite, isn't it? It's even super infinite, right? It's even bigger than the original number that's approaching infinity. Like a billion cubed is going to be a really big number, right? So we could say that this is just going to become positive infinity, right? Well, we know that the outcome then is going to be really big because we're multiplying some number times infinity, right? Everybody agree? That if I'm plugging in a really big number into negative 2 times x cubed, I know I'm going to get a super huge number, but the question is just going to be, what's the sign of that really big number going to be? All we got to do is just look at the signs of the factors. That's it. So we don't even really need to think about what those numbers are. We can just think about what their signs are going to be. So for example, what's the sign of negative 2? And it's not a trick question, it's that easy. What's the sign of negative 2? Negative, right? That's negative. What's the sign of a positive number? Sure, it's a really big positive number, but it's just a positive number. A positive number cubed has what sign? Positive. So then what's the sign going to be if I multiply a negative times a positive? It's going to be negative. See how I did that? Okay. So we can do this without having to graph it. Let's take the limit, or find the end behavior on the left. So how about this one? As x approaches negative infinity, f of x approaches what? Well, is it going to be infinitely big, the answer? And you see what I mean? I really want you to get this. I want this needs to make sense. When I say, is it going to be infinitely big, I mean, yeah, it's going to be infinitely big, isn't it? If x is approaching some infinitely large negative number, if I'm going to end up cubing that number, it's just going to get even bigger, right? So wouldn't you agree that the size of the number we're going to get back is going to be infinite? Agreed? It's just a matter of what goes there. Well, let's play the sign game. What are we going to get? As x approaches negative infinity, so f of x equals negative 2x cubed. What's that going to give us for our signs as x approaches negative infinity? The sign of negative 2 is what? Negative, and I've really just got 2 things being multiplied, a negative 2 times an x cubed. So the first one's negative. Well, what's x cubed going to be? If I take a negative number cubed, what's the sign going to be? Think about that now. A negative number cubed. It's going to be negative, isn't it? Right? A negative number to an even power is always going to be positive, because think about why that's going to be. If I take like negative 3 squared, I'm going to have a negative times a negative makes it a positive. If I have negative 2 to the 4th, I'm going to have a pair of negatives multiplied together and then another pair of negatives. There's always an even number of negatives, so they always cancel out in pairs to become positive. But if I multiply, if I take an odd power of a negative, like x cubed, the first two negative product, the product of the first two, they're going to cancel and become positive, but I got a leftover one that's always going to make that answer negative, right? So that's a rule we can always bank on. A negative number to an even power is positive, a negative number to an odd power is negative. So then this sign is going to be negative, and what's negative times negative? Positive, right? So the outcome is positive infinity. And that's what we got, right? We knew that's the case for negative x cubed or negative 2x cubed. That's just stretching it a little bit, right? The two part's just stretching it, right? It flipped the end behavior around, and we saw here, I'll put a 2 there. What's the 2 going to do? 2 is just going to stretch it out a little bit, right? But we still get, as x approaches negative infinity, the function is positive, goes positive, right? As x approaches positive infinity, it goes negative. Okay? You get the idea? Okay, so last thing, this is the part I wanted to get to. Am I going to make it? Maybe. Okay. So okay, let me see if this does what I want it to do. Okay, perfect. Okay, so here's the function we're going to look at now. Okay, I want this to... Okay, there's the function, right? 0.000001 x to the fourth plus 0.001 x cubed plus 0.1 x squared plus x. I want you to tell me there's 4 different terms in this polynomial. I've got this is what we call a quartic function, x to the fourth. I've got a cubic part, x cubed. I've got a quadratic part, x squared, and I've got a linear part, x. Which one of those is going to be dominant? Well, I've got a graph of the function right here. What's that look like? Looks linear, so it looks like that's the winner. Looks like x is the winner, doesn't it? Right, so that seems to be the dominant term. That's the one that guides the behavior of the function. Yeah, good deal. Well, let's just pan out a little bit and see what happens. Pan out. Yeah, it's linear. Uh-oh. What happened? What's that look like? That looks like a parabola. What's a parabola? Is this would be what kind of behavior? Quadratic. So that's going to be the x squared term, right? So it looks like the x squared term is winning after all. Okay. Let's keep going out a little bit and see what happens. Uh-oh. Uh-oh, what happened? Look at this. So now look at this. I got my end behavior. To the left, it's going down. The right, it's going up. Which one does that seem like? What does that seem like? That seems like a cube, right? What do you think is going to happen if I keep panning out some more? It's going to look like an x to the fourth, isn't it, right? Okay, there's an important moral to this story. If I keep panning out, I got to go a little ways, but eventually it starts to look like an x to the fourth, right? And if I go all the way out, you wouldn't even notice. Seriously, now think about this. Now, pay attention. We're almost done. This is really big. This is huge. If I went out further and further and further, that little blip right there that was everything we previously talked about would just go away. If I panned out further and further and further, it would just look exactly like an x to the fourth function at some point. You wouldn't even be able to tell that there's this other stuff going on, right? So here's what I want. Here's what I want you to take from this. When I have a function like this, what'd I do? I got rid of it. It's non-existent, yeah. So when I have a function like that, hold on. Last question I got for you. When I have a function like that and I want to look at the end behavior, so I'm looking at this thing on an infinitely large scale, which term in that polynomial is going to dominate the behavior. The biggest one, we call it the leading term. The biggest power of x is the only one that matters, right? So if I want to find end behavior, that's all you have to focus on, right?